why do some machine shops, routinely drop like $150,000 on a piece of capital equipment just to execute the exact same cuts they could easily do on a $15,000 machine?
Right. It seems crazy on paper.
It really does. But the answer, surprisingly, has very little to do with the actual metal being cut on the table. I mean, it has everything to do with the invisible compounding cost of human hands. So, welcome to today's deep dive.
Glad to be here.
Imagine you're standing in the middle of a brand new manufacturing facility. Like, the concrete floor is pristine, the three-phase power is all wired up, and you are the one holding the checkbook.
A very stressful place to be, honest.
Oh, absolutely. Or, maybe you're just scaling up a crowded, bustling fabrication shop, and you just need to increase your throughput. You have capital to deploy, and you're staring down this massive strategic decision that's basically going to dictate your overhead and your profit margins for the next decade.
Yeah.
Do you buy a CNC machining center, or do you allocate that capital toward a CNC drilling and milling machine?
It's the ultimate crossroads for literally any manufacturing business, because capital allocation in machining requires this just ruthless evaluation of your actual production volume versus what the equipment can actually do.
Right.
Like over-specifying your machine, buying this massive high-end rigid system just to do, one-off prototype maintenance tasks, that is a fantastic way to drown your operating capital in depreciation.
Just burning money at that point.
Exactly.
Okay.
But under-specifying. That means buying a lightweight machine for a really heavy production environment.
Yeah.
You just end up bottlenecking your spindle uptime and, frankly, destroying your cutting tools.
Which limits your shop's growth before you've even sent out your first invoice.
Completely.
So our mission for today's deep dive is to basically tear down the structural, the kinematics, and the operational differences between these two specific architectures. We want to help you map the mechanical realities of these machines directly to your actual business model.
Which is so crucial.
Yeah. So let's start by establishing a baseline with the more accessible option, right? The CNC drilling and milling machine. Because on paper, it sounds like the ultimate hybrid. You're merging the Z-axis thrust of a drill press with the XY planar movement of a traditional knee mill.
Right, and consolidating those operations into a single vertical footprint, that solves a massive problem for facilities with limited floor space.
Like a garage startup or something.
Exactly, because traditionally you had to make really hard choices about real estate. A dedicated drill press and a dedicated milling machine, they both eat up super valuable square footage.
Right.
And moving a raw workpiece between them, that introduces fixturing errors. But the CNC drilling and milling machine, it gives you a single coordinate system. So you fixture your raw stock once, you establish your datum, and on that exact same work table, you can execute drilling, tapping, reaming, countersinking, boring operations.
All without moving the part.
Right, without unclamping it and risking a loss of your zero. And then you can transition straight into face milling, bevel milling, slotting.
It's basically the Swiss Army knife of the shop floor.
That's a really good way to put it.
Like, it's highly efficient for getting a specific, smaller payload into orbit without needing a massive launch complex, if we want to use a rocket analogy. But it inherently has limits on absolute thrust.
Yeah, and the appeal of that consolidated footprint is really just the flexibility it offers the operator. Because these machines, they typically bridge the gap between manual machining and full CNC interpolation.
Right, because you still have the hand wheels.
Exactly. A lot of models keep the manual hand wheels on the X and Y axis. So a machinist can literally physically feel the cutting pressure during a delicate manual setup while still having stepper or servo motors for automated computer feeds via G-code.
And the sources mention mechanical power feeds too, which, for a machinist who spent 10 minutes manually cranking a hand wheel just to take this slow, boring finishing pass across a plate of mild steel.
Oh, man. It's exhausting.
Right. So a power feed bridging that gap between manual labor and CNC control, that's a massive ergonomic upgrade.
It dramatically reduces operator fatigue. And the best part is, it keeps the initial capital expenditure incredibly low.
Right. So for the listener, if you're a startup or a maintenance tool room, deploying a machine like this means you can start taking on paying jobs right away.
Yeah, you generate revenue immediately.
Yeah.
You completely avoid taking out a massive commercial loan, so you keep your overhead low, but you still have the capability to machine a huge variety of small batch parts.
Okay, so let me play devil's advocate here with a hypothetical.
Sure, go for it.
If the CNC drilling and milling machine gives me full 3-axis movement and it costs like a fraction of the price of a massive industrial machining center, why wouldn't I just use it for everything?
Yeah.
Like, let's say I need to machine a massive block of hardened D2 tool steel. Why can't I just tweak my G-code, drop my feed rate down to an absolute crawl, take microscopic depths of cut, and just chew through that steel slowly? I mean, I'm trading time for a vastly lower monthly equipment payment.
It makes sense financially, but physics will severely punish that strategy.
Oh, really? Physics.
Yeah, physics. It all comes down to the mechanics of the actual cutting wedge and this concept called minimum chip thickness.
Okay, break that down for me.
So, if you feed a carbide end mill too slowly into hardened steel, the cutting edge doesn't actually bite into the material. It just rubs.
Ah.
And that rubbing generates immense heat and friction, which work hardens the surface of the steel, making it even more difficult to cut on the very next pass.
So you're basically making the job harder for yourself.
Exactly. To successfully cut heavy steel, you have to push the tool hard enough to shear the metal. And shearing metal generates violent kinetic energy.
And because the smaller drilling and milling machine just has that lightweight cast frame, that violent energy has literally nowhere to go.
Right. It reflects straight back into the machine structure.
Which is chatter, right?
Yes, exactly. That reflected energy manifests as harmonic resonance. Everyone on the shop floor knows it as chatter. And chatter is incredibly destructive.
It's not just a bad sound.
No, it's not just that loud screeching. It's the physical vibration of the tool rapidly bouncing off the workpiece. Those micro impacts will shatter the brittle cutting edges of a carbide insert in minutes.
Wow.
It'll completely destroy the dimensional accuracy of your part, leave a terrible surface finish, and if you push a lightweight machine column past its limit, those vibrations can literally cause microfractures in the casting itself.
That's wild. So the column and the base of the smaller machines, they're really just engineered for the cutting forces of aluminum, brass, maybe mild steel.
Exactly. They use standard dovetail ways or lighter linear guide rails. They're absolutely not engineered for the sheer mechanical trauma of continuous heavy metal removal.
Okay, so to safely absorb that trauma, you have to step up to the CNC machining center.
You do, because those are heavyweight structures, usually poured from high-grade mehanite cast iron.
Mehanite. What makes that different?
Well, the crystalline structure of this specific cast iron contains these graphite flakes that basically act as a microscopic, shock-absorbing matrix. It naturally dampens harmonic vibrations.
Oh, I see. So instead of the energy bouncing back into the tool and shattering your end mill, the massive iron base of the machining center just swallows the kinetic energy whole.
Precisely. And the geometry of the moving components is entirely different, too. Instead of those light linear rails, heavy-duty machining centers often use massive boxways.
What are boxways exactly?
They're essentially solid rectangular blocks of cast iron that slide within matching channels. And they maintain this microscopic layer of hydrostatic oil right between the surfaces.
So it's metal riding on oil.
Yeah. And that massive surface area provides immense rigidity. It acts as a fluid damper against the cutting vibrations. So the spindle can literally bury a huge cutter deep into a block of steel without even flinching.
And the work tables have to reflect that too, right?
Oh, absolutely. A big boxway machine requires a thick, heavily ribbed cast iron table because it has to support the dead weight of multiple heavy steel vices, hydraulic clamping fixtures, and the raw stock itself, which, could weigh thousands of pounds.
So you're basically matching the structural mass of the machine directly to the physical demands of your daily workload.
That's the golden rule.
Okay, so once you upgrade to a machine with enough iron to handle continuous, aggressive cutting without stopping, the entire production calculus changes.
It really does. Because the machine is no longer the limiting factor.
Right, the latency in your production shifts away from the spindle and directly onto the human operator running the machine. Which brings us to the most defining architectural difference between these two systems.
The game changer.
Yeah, the single component that separates a basic milling machine from a true machining center, the automatic tool changer, or ATC.
The ATC fundamentally alters your overall equipment effectiveness, your OEE. Like, structurally, a CNC machining center is really just an incredibly rigid milling machine. But the integration of a tool magazine and an ATC that elevates it into an entirely different category of automated production.
Let's actually map out the cycle time math of running without one, just to put it in perspective for the listener.
Good idea.
If you're running a standard CNC drilling and milling machine, every single tool change requires the spindle to halt completely. The operator steps in, manually backs off the drawbar, pulls out the tool holder, grabs the next drill or tap, puts it in, tightens the drawbar, touches off the tool height, and finally hits cycle start.
And even an incredibly fast machinist is going to take 30 to 40 seconds to complete that swap and verify it.
30 to 40 seconds per tool.
Yeah. So if your part requires, say, a center drill, a standard drill, a chamfer mill, a tap, and a finishing end mill that is 5 manual interventions just for one part.
Wow. So if you're running a batch of 200 parts, your spindle is sitting completely idle for over 16 hours across that run, just waiting for a human hand to turn a wrench.
16 hours of zero productivity.
It's like having an invisible assistant handing you tools at lightning speed versus having to stop everything you're doing to dig through your own toolbox every 5 minutes. Or, in manufacturing terms, it's like a computer processor fetching data from a slow hard drive instead of his own high-speed cache memory.
That is a perfect analogy. The processor is incredibly fast, but the retrieval latency destroys the computing speed. The ATC acts as that high-speed cache.
And the mechanical elegance of these ATCs is just staggering.
It really is. The most common industrial design is the twin-arm, cam-driven mechanism. So while the machine is busy cutting your part with tool number 1, the CNC controller is already rotating the tool carousel in the background to pre-stage tool number 2.
So when the G-code calls for the tool change, there is zero searching.
Exactly zero. The spindle stops and orientates, the twin arm swings in, grabs the tool in the spindle and the pre-stage tool in the carousel simultaneously, drops them down, rotates 180 degrees, and just rams the new tool into the spindle.
And that whole sequence takes what?
Less than 3 seconds. The spindle spins back up and the machine just keeps cutting.
Incredible. So you clamp the raw material into the vise once, press cycle start, and the machine handles the entire sequence completely unattended.
Completely unattended. The operator can literally walk away. They can program the next job, do quality control, or run a second machine at the same time.
And that is the crux of the capital allocation debate.
Right there. The manual nature of the cheaper drilling and milling machine is perfectly acceptable for a prototype shop doing one-offs, because the operator's manual tool change time isn't the primary bottleneck when you're only making one single part.
Right, you're not losing 16 hours on one part.
Exactly. But in a high-volume production environment, the ATC's ability to drive continuous, unattended spindle uptime, that is what instantly justifies the massive price tag of the machining center.
Because eliminating the human latency pays for the machine.
It pays for itself, yeah.
But, spindle uptime and heavy metal removal rates, they mean absolutely nothing if the geometry of the final part is wrong.
Very true.
Like, speed is entirely irrelevant if you're just making scrap metal really, really fast. So let's look at the final critical metric we need to cover, the accuracy and repeatability of the cut.
Because controlling dimensional deviation is really the core metric of modern machining.
Right.
When an engineer drafts a part, they apply specific geometric dimensioning and tolerancing, and matching the kinematic accuracy of your machine tool to the specific tolerance bands of your industry that ensures you aren't overpaying for precision you don't need.
Or failing quality control on parts you actually do need.
Right, which is even worse.
So the sources highlight that a standard CNC machining center maintains extremely tight tolerances all day long. And that isn't just because of the heavy cast iron, right? It comes down to the drive mechanisms, too.
Yeah, the guts of the machine. Industrial machining centers utilize closed-loop servo systems and these massive recirculating ball screws.
How is a ball screw different from, like, a traditional lead screw?
Well, a traditional lead screw relies on sliding friction, which inherently develops mechanical backlash over time. It gets sloppy. But a ball screw uses tiny steel ball bearings to translate rotary motion into linear motion.
Oh, so it rolls instead of sliding.
Exactly, which virtually eliminates backlash.
And you mentioned it's a closed-loop system, which means the machine actually knows where it is at all times, right?
Yes. The servo motors rely on high-resolution rotary encoders, or even physical optical glass scales mounted directly to the machine axis.
Scales.
Yeah. So if the CNC controller tells the table to move exactly 1 inch, the glass scale reads the physical movement and sends feedback to the controller, confirming that it moved exactly 1.0000 inches.
And what if it gets hot? Like, doesn't metal expand?
It does. But if thermal expansion in the ball screw causes a deviation of even 1/10 of a thousandth of an inch, the controller sees it on the scale and immediately compensates for it.
That is insane. That level of microscopic control, I mean, that's mandatory if you're machining titanium turbine blades for the aerospace sector or, highly regulated titanium bone screws for the medical industry.
Oh, absolutely. The 1,000th part off the production line must be dimensionally identical to the very first part. Deploying anything less than a closed-loop machining center for those sectors just results in unacceptable tolerance, stack-up, and rejected parts.
Which brings up a critical point regarding the smaller CNC drilling and milling machine, because the source material states that these versatile machines offer what is classified as IT8 level accuracy.
Yes, IT8.
So for a listener trying to evaluate their capital purchase, what does the IT8 tolerance grade actually mean in practical physical dimensions? Because it sounds, I don't know, almost like a downgrade. Is it bad precision?
Not at all. It's not bad precision. The IT grade, the International Tolerance Grade, is an ISO standard used to quantify manufacturing precision based on the size of the part.
Okay.
IT8 is a very standard industrial tolerance. To put it in physical terms, if you're machining a feature that is 50 millimeters across, so about 2 inches, an IT8 tolerance band allows for a deviation of roughly 46 microns.
46 microns. Okay, so in American shop terms, we're talking about roughly 1.8 thousandths of an inch, so almost 2 thou.
Correct, and a variance of 2 thousandths of an inch is a fantastic capability for general manufacturing.
It's plenty tight for most things.
Oh, totally. It is highly sufficient for creating press fits for standard bearings, machining general hardware, fabricating automated packaging machinery, or, executing agricultural equipment repairs.
Right, it provides smooth surface finishes and reliable geometric fits. I mean, you don't need a $500,000 machine holding sub-micron tolerances just to mill a replacement bracket for a John Deere tractor.
Exactly. Attempting to hold sub-micron tolerances on agricultural repairs is just an absurd waste of resources. IT8 perfectly satisfies the vast majority of mechanical needs across the globe. It really just excludes the machine from extreme aerospace, high-end injection mold making, or precision optics manufacturing.
Right. So pulling this all together for the listener, standing on that pristine factory floor, holding the checkbook, the decision ultimately boils down to a brutal, honest assessment of your daily workload.
It really does.
You cannot deploy a lightweight, IT8-rated CNC drilling and milling machine onto a heavy aerospace production line and expect it to survive. The structural resonance will destroy your tooling, and the manual tool changes will absolutely destroy your cycle times.
You'll bleed money.
Yeah.
Yeah.
But conversely, sinking $200,000 into a massive boxway machining center just to drill and tap aluminum brackets for a couple hours a day, that will starve your business of the capital it needs to actually grow.
You have to match the density of the iron to the density of the material. And you match the kinematics of the automatic tool changer to the volume of your production runs.
But, if we look beyond the mechanical constraints of today, just to leave you with a final thought here, the evolution of these machines presents an entirely new variable for capital allocation.
Oh, the software side?
Exactly. We spend so much time debating the physical mass of the iron and the mechanical speed of the tool changer, but the next massive leap in machining isn't happening in the casting foundry at all, it's happening in the software.
Yeah, digital twins.
Right. Consider the rise of digital twins and AI-driven thermal compensation. We were literally entering an era where advanced edge computing can map the specific thermal growth and harmonic resonance of a cheaper, lighter machine in real time.
And dynamically alter the G-code microsecond by microsecond to compensate for the machine's physical shortcomings.
Exactly. So if software can eventually force a $50,000 machine to hold the tolerances of a $200,000 machine, how will that entirely rewrite the rules of capital allocation on the shop floor?
It's going to disrupt everything.
It really is. Something for you to think about the next time you watch a spindle spin up. Thanks for joining us on this deep dive.